Okay, for our next L'Hopital's rule problem, we're going to look at this following one-sided limit. And by the way, there's nothing special about the fact that this limit is one-sided. Could have been two-sided, but for simplicity, we're just looking at the limit as theta goes to pi halves from the right. So first, we want to analyze the indeterminate form. So what do we have when we consider our two functions separately? So we have the limit as theta goes to pi halves from the right of tangent theta, and if you recall your graph there, what do we recall? That should go to minus infinity. And if we have the limit as theta goes to pi halves from the right of secant theta, now notice I'm not including the minus in this analysis. We're just looking at this function and this function, and I'll bring the minus in a second. This is also minus infinity. Let me show you the graphs. Okay, so here, as an illustration, here we have the two graphs. Theta rather, is going to pi halves from the right. So in that case, where is the limit going? Down to negative infinity, as we said. This is for the tangent function. Now for the secant function, once again, I've got the pi halves drawn, theta equal pi halves drawn vertically again. So as theta is going to pi halves from the right, where is the limit of secant, which is 1 over cosine? It's also going to minus infinity, which is what I have here. So when we look at this form, you may think it's minus infinity minus infinity. That, of course, would not be indeterminate. But here, notice we would have minus infinity minus, that's this minus, negative infinity, and that's effectively infinity minus infinity form, which is indeterminate. Good. So this is one of the indeterminate forms that we're learning to consider. And now what do we do here when we have such a form? Well, we need to convert this to some sort of fraction if we are going to try L'Hopital's rule. So let's see what we've got. And what's the simplest thing that comes to mind? Well, let's write the trig functions in terms of sine and cosine. So tangent is sine over cosine. What is secant? 1 over cosine. And now this gives us a simple function to consider. And once again, notice at each stage, you always write the limit at every stage in the limit problem until you're evaluating the limit by direct functional evaluation or perhaps some theorem. And there are only a few theorems that we have that aren't where the function is continuous at the value, which it's certainly not now. Okay, so now what do we have in this rewritten form? Once we rewrite it, you're now honor bound to analyze the form. So here the numerator is going where? Sine of theta is 1, so this is 1 minus 1, which is 0. The denominator, looking at it separately, the cosine of pi halves is 0. So what form do we have? 0 over 0 form. And in my previous videos, I didn't pay much attention to, because I analyzed it kind of mentally or visually. But there is other criteria you have to worry about, is the derivative of the denominator can't be 0. Of course, you're going to say it's 0 at infinitely many points. Of course it is, but not near pi halves. We can isolate, we can find an interval around pi halves where the denominator, the derivative of cosine, which is sine, negative sine, is not 0 in that interval again discounting what may or may not be happening at pi halves. Okay, so the derivative of sine of theta is cosine of theta. The derivative of 1 is 0, and what's the derivative of cosine? Minus sine, and again this one we can evaluate directly. I'll move the negative into the numerator, and when I meant directly I meant by functional evaluation. This is cotangent, by the way, in case we cared. And now what's the cosine of pi halves? That's 0. What's the sine of pi halves? That's 1. So this answer is 0. So infinity minus infinity form, we did the most natural thing, converting it into its basic trig components to get the quotient that we were looking for, and then we could of course apply L'Hopital's rule because it had one of the appropriate forms, which is 0 over 0. Okay, now let's look at this one. This one's another form we haven't seen in terms of this video series yet. So what we have here, let's look at our two pieces. We have the base and the exponent. So let's look at our base of this exponential function. So the limit as x goes to 0 from the right of sine x, that's just 0. And our exponent that we're considering, which is the square root of x, what's happening there that's also going to 0. So what form do we have? Well, the base is going to 0, the exponent's going to 0, so we have form 0 to the 0, which is an indeterminate form. Again, why is it indeterminate? Because just by noticing that fact, you can't say anything about the limit. It could be non-existent, it could be the number 1, it could be the number e, it could be basically anything it likes, so what we have to do is figure it out using some analytical technique. Alright, so what we want to do, there are many ways to write this, but basically we're going to use a logarithmic technique. First, what we want to do is let y, this is a common technique that we use for limits that you may have seen in Cal 1 a few times. Let's let y be the limit we're looking for, and now the goal is to find y, and of course we do this oftentimes when you're going to do some sort of manipulations to the limit, and that's what I'm about to do next. So now if y is equal to this limit, and again technically you could say we're actually assuming that the limit exists, and we're going to take the natural log of both sides. Okay, now the natural log is a continuous function, so the natural log will go to the inside. So now we'll have the limit as x goes to 0 from the right. Now again, you may be saying, well, the natural log is a continuous function, but we haven't evaluated the limit yet. But as 0 to the 0 form, the lowest this number would be 0. We're having positive values to positive exponents, so it's positive at all values except 0. So there's really no problem. The natural log is continuous on the open interval 0 to infinity. So that's really what aids us in that making this move of bringing the natural log inside, if you like. And if really you don't like it, there's another way we could rewrite this to avoid this step. So it's not really a problem. Okay, so now we're going to use properties of logs to bring the square root of x down. In fact, let me rewrite this to give us a little more room. It's going to take it just a few more steps to do the problem. So this will be the limit and now the square root of x comes down times the natural log of sine x. Now what do we have to do here? Well, let's look at what we've got. Here, this piece is going to negative infinity. Remember, sine x is going to 0 because x is going to 0. And remember your graph of the natural log. As x goes to 0 from the right, the natural log goes to minus infinity. And so this piece is going to 0. So you have 0 times infinity form, which is fine. But this tells us that we need to rewrite that. Again, you want to take the reciprocal and write one of these terms in the denominator. And as I've indicated before, oftentimes you'll make that move on the algebraic piece. So this is x to the minus 1/2. Now remember, it's really 1 over the square root of x in the denominator. I'm writing it this way to facilitate the derivative, but let's analyze the form at this stage. Well, this is negative infinity, but it's infinity over infinity form. We've already agreed that this piece is going to infinity, technically negative infinity. Now what happens to 1 over the square root of x? Well, as x goes to 0, the denominator goes to 0. The numerator, I'm just looking at here, the numerator stays at 1, so this goes to infinity. So we have infinity over infinity form. We can apply L'Hopital's rule. Let's see what we've got. Now we can apply L'Hopital's rule, take the derivatives of the numerator and denominator separately. Now what's the derivative of the natural log of sine x? Well, that's cotangent, but it's 1 over the sine of x times, then here comes the chain rule, the derivative of sine, which is cosine, so that's actually cotangent if you were thinking about it. And now the derivative of the denominator is just negative 1/2 x to the minus 3/2. So let's simplify this function before we attempt to analyze it. So this would be negative 2 out front. The reciprocal, the negative 1/2 will flip, so to speak, in the denominator. We have x to the 3/2 cosine x over sine x. Now again, this is 0 over 0 form. Which means we can apply L'Hopital's rule again. We don't really want to mess with the product rule here, although it's not a problem. I guess we can. I was going to separate it, but let's go ahead and do it in a slightly more straightforward fashion. Alright, let's see what we get. Alright, so it's 0 over 0 form, which says we can apply L'Hopital's rule. Now we have a product rule for the derivative of the numerator. So it's 3/2 x to the 1/2, derivative of the first term times the second, plus the derivative of the second. Remember now, this is not the quotient rule. So this would be minus sine x times x to the 3/2 over cosine of x. And now that we're home free now. Why? Because the denominator is no longer 0. What's the cosine of 0? That's 1. So when it comes to this limit, we can evaluate functionally. We have 1 on the bottom. And now what's the square root of 0 is 0. So this whole piece is 0. And the same thing here. Both of these terms are 0. Even this piece is 0. 0 plus 0 is 0. So we have 0. We have 0 over 1, which is just 0. Now, let's read what we have very carefully. So what is our answer? Now, it's not y. We're looking for y. We don't have that. So let's see what we've got. We're 2 steps away. So thus, we've shown the natural log of y is equal to 0. That's just recopying all of this. If you read it, the natural log of y is equal to what? 0, which is what I have here. Now let's exponentiate. We have e to the natural log of y. So this would imply that y is equal to e to the 0. And what's e to the 0? That's 1. Now, so we have y equal 1. Why does that answer our problem? Well, y was equal to the very limit that we were looking for. So the final answer to our problem, the original limit, is equal to 1. So let's look at this problem, the limit at infinity, and let's analyze our function. So what is happening in the numerator? Well, the numerator goes to infinity. The denominator is dominated by the 3x term. It goes to infinity. This will have no impact. This sine term oscillates between 1 and -1. So this problem does in fact have a good form for us to start. It has infinity over infinity form. So let's try L'Hopital's rule. So I'm recopying the original problem. And now this will be where we apply L'Hopital's rule, the derivative of the numerator. We take the derivative of the numerator and denominator separately. So what's the derivative of 21x? That's just 21. What's the derivative of the denominator? 3x minus sine x, that's just 3 minus cosine x. Now let's take a moment as we do and let's analyze this function in terms of where the limit is going, and that's where we have a problem. The numerator is constant. It's staying 21, but what happens to the denominator here? Now this one doesn't go to any one number. This function will oscillate between 4 and 2. So this limit does not exist. So this equal sign is a lie, so to speak. And that means that's what you cannot apply L'Hopital's rule. And so this calls into question, the way we work these problems, because we put the equality there before we were done evaluating. And that's okay, it's kind of the style that we use, but we just have to be aware that if this limit, after you take the derivatives, does not exist, it has to be a finite number, or it can go to infinity, and then you can make a claim about the limiting value of the original function at the appropriate value under consideration. But if it doesn't exist, then you actually don't get this equality. We can't say using L'Hopital's rule whether this limit does not exist or exists. In fact, we could do it with the calculus 1, the classical approach. So let's go ahead and work it as you would in using the limit techniques that you would learn before L'Hopital's rule. So let's take our original problem and let's multiply by 1 over x over itself. Many of y'all are saying, okay, yeah, this technique is coming back to me. This is one of the techniques that you would use when identifying horizontal asymptotes, which is exactly what we're doing when we're considering a limit at infinity. Okay, so you have 21 in the numerator, and now you have 3 minus sine x over x. And now, since both of these exist, and again I'm getting ahead of myself, but since both of these exist and the denominator is non-zero. If you like, we can write it like this for effect so you can see what's happening. If it's been a while since you've done the Calculus 1 technique, you pass the limit to the numerator and denominator separately. So, let's see what we get. Now we can evaluate both pieces. This is 21. Now as x goes to infinity, where does 3 go? Well, it's constant, it goes to 3. Same reasoning we had here, why this went to 21. Now, what about sine x over x? Now, again, technically this is a squeeze theorem result, but you have the bottom going to infinity. The numerator's trapped between -1 and 1. So by the squeeze theorem, that's going to go to 0. Again, now I'm not saying in terms of this problem that there's nothing to show there. Analytically, there is. But we're interested in kind of L'Hopital's rule at this time, so I'm kind of focusing more on those techniques. So that's equal to 7. I'll have a separate video on evaluating that limit with squeeze theorem that you can click over and look at if you're interested to see precisely how this worked. Remember, calculus is a course about analysis and it's about analytical techniques, so you really do want to make sure you understand why that limit is 0. But in any event, this is the classical method. The key here, here's our first example where after you take the derivative, you can't claim that what is obtained is equal to, in the limit, to the original problem at hand, because this limit doesn't exist. Kind of last problem, throwing a problem for fun here. Look, so this is a kind of an easy one to analyze by this point. What's our form? Well, what's the tangent of 0? 0. So 0 to the 89 would be 0. And x to the 85 at 0 is 0. So this simply has form 0 over 0, but who would want to try L'Hopital's rule on that? Let's try it, and we'll abandon it pretty much straight away because it won't be fruitious. Okay, so here's the original problem. So let's try L'Hopital's rule. It has the right form, so it has the correct form. So what would we get? Well, let's first off, the tangent derivative is not bad. Chain rule, of course, but 89 tangent to the what? 88, subtract 1. And now, of course, times the derivative of the inside, which is secant squared. Still no problems. And then, of course, 85x to the 84. So it got better, but only marginally so. And there's no question this has 0 over 0 form again. And you can probably see what would happen. You're going to probably have to apply L'Hopital's rule 84 more times, and each time, remember now, this derivative was fairly simple, but now look what you have, and we don't care about the constants. The constants will move outside, but now you've got a product rule with chain, of course, embedded. But then when you try those 85 consecutive derivatives in the 85 consecutive applications of L'Hopital's rule, the numerator, it becomes increasingly more complex. You get more and more terms. It becomes unwieldy, really, after 2 more derivatives for sure, for most people. Okay, so this isn't very fruitful, and I'll have some other videos which will show some of the complexities of where L'Hopital's rule, while applicable, isn't necessarily, it's not fruitful to apply. So let's do it with, again, a classical Calculus 1 technique. Let's call it a classical technique, and by classical I mean kind of straight limit methods, no application of L'Hopital's rule. So let's see, what do we have? Let's get our original function. Let's separate. You could do 2 things. We can multiply by x to the 4 over x to the 4 if you like that, or we can just separate out the 4 of the tangent functions, whichever one you want to do their equivalent in nature, the work will look a little different. Alright, so let's separate. Some of y'all would like that better than multiplying in, although there's nothing wrong with it. And I think you're seeing what I'm going for. It's not mysterious that I've gotten an exponent of 85 there, because what exponent do I have in the denominator with the x? Now these match. That's going to be very helpful for us. And I'll use, if you want, I can use L'Hopital's rule in this hybrid technique, but I kind of called it the classical method, and if we can work it with L'Hopital's rule if you want, so it would be kind of a hybridized method. Okay, so now let's separate this limit into two pieces. And now this, if you're paying close attention, this has the same flaw. It's not a flaw, but the same little problem as we did in that case where we couldn't apply L'Hopital's rule. You're not supposed to separate until you know that the limit of both pieces exists, and we certainly don't know that yet because I'm still in the middle of evaluating them, but nonetheless, this is how we write these problems. We could just go to the side and work these out, but most people don't like that. Alright, so far so good. Now, of course, what is this limit? 0. Now again, if this limit doesn't exist, then this separation here would not have been valid. And so we keep working until we make that determination. And basically, if it does exist, I'm talking about this limit, then we say, hey, everything is fine, and this separation was justified. And again, that's just how we tend to write the problems in this form. It's not, strictly speaking, 100% perfect, but it's common in terms of the style. All right, now that these exponents are the same, I'll do it in 2 steps so you can see it. We'll write this whole problem to the 85th. Alright, so now, and I'll do it like this. I guess I'll go L'Hopital's rule on this problem just for fun, so you can see how we might have to do several manipulations to get it to a nice point. Alright, now the x to the 85th function is continuous, the power function, so the limit will pass to the inside of that function. And now look at just where the limit is. This is a simple problem. The 85 is now outside. So this 85 doesn't take effect until after you evaluate this limit. And now in my style, I like to evaluate the limits at the same time. I don't like to evaluate this because it's 0, and then you say, okay, this piece is 0, and then you're tempted to say 0 times anything is 0. That's what's going to happen. But we don't quite know that yet. So I like to just wait and evaluate at the end. So let's analyze this form. This is 0 over 0 form. Tangent of 0 is 0 as x goes to 0, and of course as x goes to 0, x goes to 0. Alright. So now we're applying L'Hopital's rule only. We're only applying L'Hopital's rule to this piece highlighted in yellow, and I'll draw a box around it. Okay, so now again I'm going to, kind of what I call good form, I'm just going to keep the limit here until the end where I'll evaluate all the limits separately, but at the same, writing them at the same time. Alright, so now L'Hopital's rule, and I'll put the result in here for what this piece that I have highlighted in yellow. Alright, what's the derivative of tangent? Secant squared. What's the derivative of x is 1. And still we have this 85. Okay, now there's no longer a problem with this one. Secant of 0 is 1, and we have a non-zero value in the denominator. So now we can just evaluate both pieces by functional evaluation. So for the first piece, where is this limit going? So let me highlight this in green so we can keep track. Alright, so for this piece or factor in green, where is that limit going? That's going to 0. Okay? Now where is this piece in yellow going? Well, don't forget, the limit's taking place inside those parentheses. So now this is just 1 over 1. And that's the result of the limit highlighted in yellow. What's 1 to the 85th power? Just 1. And that's 0. And that's our final answer. So that's kind of an interesting problem where we hybridized it. We didn't want to try to mess with L'Hopital's rule as written because it would have been intractable. So then we rewrote it, re-separated out, and dealt with a piece that was much nicer to handle in L'Hopital's rule, which was just this piece right here. And I could have done this piece using Calculus 1 methods. Because I referred to that, I would have done this as the limit as x goes to 0. What's tangent sine over cosine? So I would have rewritten this thusly, and then I would have separated again this, and I would have separated out the cosine, because we have one of our first favorite theorems in Calculus 1 is this limit is 1, and that's proved by squeeze. But if I would have not gone for L'Hopital's rule and I would have stayed purely in a classical Calculus 1 motif, I would have separated that out. Again, still all inside the parentheses with the exponent to the 85th power, and work that out thusly. Okay, I hope you enjoyed this video, and this was the second part in the L'Hopital's rule series. There'll be a third part where I'll do a few more challenging problems. The second video, these were a little more challenging. I'll do an infinity minus infinity over infinity form, which is a little bit interesting. And I'll show you a couple more problems like this one, where L'Hopital's rule, coming straight at it with L'Hopital's rule, is not productive. So you want to try other techniques. And what that says is, once you get a big gun, which is a big technique such as L'Hopital's rule, it's not the end-all and be-all. You will still need to be able to go back and do limits without it, because sometimes taking those derivatives just isn't very helpful. Alright, thank you very much. We'll see you next time.